Okay. So questions from today's sections.
We're just going over which ones are versus.
Okay. So we might as well create the table of, because these were the end of the addition reactions. So only addition reactions can be Markovnikov or anti-Markovnikov. So forming the epoxide is not Markovnikov or anti. It's a different kind of reaction. So only when we're adding two things across the double bond can something be Markovnikov or anti-Markovnikov, or neither. So let's go ahead and we can create that table if my little pen will work. Okay. Okay, so all right, so our first thing is our reagent, are what we're adding, the two groups we're adding, whether it's Markovnikov or anti-Markovnikov, whether it's cis or trans, and then we should probably have a table for notes or a column for notes. Okay, so I'll give you the reagent, you help me fill it in. By help me fill it in, you fill it in. So we started with HX. What am I adding? Well, I should get out the wheel. That's the one I would have chosen to answer because that's the easiest one. So we're adding H and X. And X is chlorine, bromine, iodine. We don't normally mess with HF as a reagent because HF, have I ever talked about HF before? Let's see, yesterday was what, mercury? So HF is what they use to etch glass. HF is a really strong acid. If it gets in your bloodstream, it will change your pH of your blood, which is never a good thing to do if you want to live. So we normally just do iodine, chloride, and bromine. So is it Markovnikov or anti-Markovnikov?
No.
Okay, it's Markovnikov. Cis trans 50-50.
Hannah.
Okay. Any notes on this? I'll fill in the notes. So one of the things we should say is, why is this 50-50? And it's because it goes through what kind of an intermediate? It goes through a carbocation intermediate, and one of the things that we equate with a carbocation intermediate is its sp2. So in other words, when you have an intermediate that is trigonal planar with the unhybridized p orbital, whether that has nothing in it for a carbocation or a dot for a radical, you're always going to get 50-50. So you can remember kind of, it's always going to be 50-50 when it goes through an sp2 hybridized intermediate. So that's always going to be the case. And the notes, when I put in notes, I think of, okay, you know, when we get to reactions that have a triangular intermediate, what's the significance of that? A triangular intermediate means that the reagents are going to add 100% trans. Square intermediate, 100% cis. So, all right, then we did H plus H2O. So what did we add there?
Cameron.
Okay, we added H and OH. And Markovnikov, anti-Markovnikov.
Eleanor.
Now you seemed a little hesitant on that. Let's see if we can go beyond memorization here. So what kind of intermediate is this one going to undergo? H plus H2O is going to have what kind of intermediate? I'm going to take the double bond and I'm going to react it with the H plus and form what kind of intermediate? A carbocation intermediate. So have we had any reactions where we formed a carbocation intermediate that were not Markovnikov? So the C plus intermediate is not only going to give us a particular orientation, it's also going to give us Markovnikov. So whenever you undergo a carbocation intermediate, it's always going to be Markovnikov addition. And then cis trans.
Calais.
Kaylee. It doesn't say your name right. 50-50. Why? Because it's undergoing, it goes through a carbocation intermediate. Okay. Now, remember anything with an H2O can also be replaced with, that H2O can be replaced with an HOR, with an alcohol. So instead of adding H and OH, we're going to add H and an OR. We're going to add the alcohol across the double bond. Then what was next? What was next was BH3, H2O2. So what did that add?
Megan.
H and an OH. And
Max.
anti-Markovnikov. Oh no. It basically takes pieces away. So every time you get called on, it removes you from the list. But then the last person on the list doesn't get called on. So, where did my table go? What is it? 100% what? It's either cis or trans. 100% cis. Remember, this intermediate has the boron attached to the carbon, and then the carbon-carbon double bond, and then there's the H, so it basically forms a square transition state. And the boron goes to the carbon that is least sterically hindered, which sets up the anti-Markovnikov, and then the square intermediate sets up the 100% cis. Okay. And then all the other ones are from yesterday and today. So Br2, what are we adding?
Calais.
2 BRs, BR and BR. Markovnikov, anti-Markovnikov.
Megan.
Or neither. We'll call it neither. Because when you're adding the two groups that are the same, there is no Markovnikov. Now, you are correct that it's going to be Markovnikov in the fact that the Br plus does add, but with Br minus, we end up with 2 BRs. We don't know which one added first. So the next reaction is going to be Markovnikov when we modify this. And these 2 BRs are going to add
Greg.
100% trans, and the reason that they're adding 100% trans is because we have what kind of intermediate? We have a triglyceride. So then our next modification of that was Br2 and water, although we could substitute an alcohol for the water. And so what are we adding here?
Max.
A BR and an OH. And if we use the alcohol, we would add a BR and an OR group.
Aishwarya.
So Markovnikov, anti-Markovnikov. So the BR plus in this case is our electrophile, and this is going to add Markovnikov. In terms of the BR plus going to the carbon with the most hydrogens. And then this one's going to add
Eleanor.
This is a very similar reaction to what happened above. It's 100% trans. Because this goes through that bromonium ion intermediate. So again, it goes through the bromonium ion intermediate. The only difference between numbers between the 2 and 3 is those two bromine reactions is, in the first case, there's no other nucleophile attack. In the second one, there's a solvent right there, able to attack, and so that's where the OH or the OR comes from. Okay. Let's see, what else did we have from yesterday? We had oxymercuration, demercuration. So mercury acetate, and followed by sodium borohydride. So what would be what are we adding here?
Hannah.
Okay, so initially we're adding a mercury acetate and which will become a hydrogen. And what's the second thing we're adding? Sorry, it should be mercury acetate, water, and then we're adding the OH. So initially we add a mercury acetate and a water, and then that mercury acetate becomes an H with the sodium borohydride. So net result is we're adding H and OH.
Brandon.
So then Markovnikov, anti-Markovnikov.
Alex.
Okay. Let's see. Cameron, you're last in this round. So, okay. 100% trans. Why?
Because it goes through the triangle
With the mercury acetate. So it undergoes the mercury acetate triangular intermediate. Making epoxides does not fit this addition because I'm basically adding the same thing. And then our last one for yesterday was hydrogenation with either palladium or a platinum catalyst. They are important. So what am I adding in the hydrogen case?
Brandon.
We won't make you answer right off the bat. So when we add hydrogen,
Alex.
two H's, okay? Markovnikov, anti-Markovnikov? Neither, because it's two of the same groups. So it's neither Markovnikov or anti-Markovnikov. 100% cis, 100% trans. 100% cis. And then why is that? Because basically on the surface of on the palladium surface we have hydrogen atoms, and then our double bond adds on top of that, so we have a square intermediate. And so that was everything. Those were all the additions through yesterday. In today's it looks like there's just one, because we had talked about the anti-Markovnikov addition with the, oh wait, that's not on the list. Okay, we got two more. We have HBr and H2O2, hydrogen peroxide. So what are we adding there?
Aishwarya.
I'll give you the H and the BR. So all I'm doing is adding peroxide to the HBr. And what's that going to change? So it's going to turn into a radical reaction, which is going to change the final product. How? It's going to become anti-Markovnikov. So it's going to be anti-Markovnikov. Now this goes through a free radical intermediate, which takes me back up here, because a radical is an sp2 hybridized intermediate. So how are the H and the Br going to add? 50-50, because we're going through a radical intermediate, which again means that when the radical adds, it can add 50% to the top, 50% to the bottom. There's no preference for it adding to one or the other. Now, we had talked about that last week, and it's in this section. It was in this section again. So, did that reaction make sense to everybody? Since it was in today's group. And then the final addition from today is syn, what they call syn hydroxylation or syn dihydroxylation. I sometimes will call this cis hydroxylation. And there's two reagents we can use with this. We can use osmium tetroxide and hydrogen peroxide, or we can use KMNO4, and I usually say KMNO4 and base. So we use KMNO4 and hydroxide. So what are we adding here? It's going to be two OHs. So it's going to be two OHs that I'm adding. That's what the cis, well, the cis hydroxylation means that the two OHs are going to add 100% cis. So we should probably write that over here, 100% cis. And I can explain the difference between cis and syn in a minute.
What is this called?
This is called cis hydroxylation. It's also called, in the book they use the generic term syn, and then they put a DI in front of it to say syn dihydroxylation. That's supposed to be a D. So I'm going to add two OHs, 100% cis, and Markovnikov, anti-Markovnikov with this. I'm adding two OHs, so it's going to be neither. So it's going to be neither. And so why would this, why do the two OHs add cis? What kind of intermediate do we have here? What? Yeah. Although square would give me cis. It's definitely not a triangle. So what happens here is, let's use the osmium tetroxide. Osmium tetroxide has the osmium with double bonds basically to each of the oxygens. Osmium is way down on the periodic table over there somewhere. It's number 76. So it can form 1, 2, 3, 4, 5, 6, 7, 8 bonds. That's allowed for osmium. Because it's got a lot of it's got some d orbitals that it can use. Plus, plus it might have some f's too. So what happens with the osmium tetroxide is that we can write our arrows looking like this. We can write the arrow of the carbon double bond moving to form the CO bond. Then the pair of electrons from the osmium oxygen double bond goes to the osmium. Then the pair of electrons from the osmium double bonded to the oxygen goes to now form the CO single bond. And so our transition state for this, and actually we don't even have to write the transition state, we can write the final product. The final product is going to have each carbon attached to an oxygen of the osmium, like this, and then the osmium over here would have 2 double bonds. So the kind of intermediate that it undergoes is actually a 5-membered ring, which is new. So the 5-membered ring then is not big enough. If these carbons were attached to a ring, the osmium tetroxide, the 5-membered ring is not big enough to add an oxygen to the top face of the ring and then go around and add it to the bottom. A 5-membered ring's not big enough to do that. And so in this case you have to add these 2 oxygens, which will become the 2 OH groups. Those have to be cis. So they have to add, basically, if I make these both bold wedges, they have to add to the same side of the double bond. So squares and 5-membered rings are all cis, are all 100% cis. Now, what kind of reaction is this from the organic molecule standpoint? Is this an oxidation or is this a reduction? Because well, the organic has to be oxidized if it's oxidation. The osmium is being reduced, right? It's opposite. If something's being oxidized, the other reagent's being reduced, or vice versa. So this is actually an oxidation reaction. Now, in asking that question, you may go, I don't remember that. Those of you that were in lab last in summer 2, then we had that whole controversy about reductions and oxidations one day. But what does oxidation mean? So in organic chemistry, it is sometimes easier to keep track of oxygens and hydrogens. Actually, it's always easier to keep track of oxygens and hydrogens than it is to keep track of electrons. So oxidation means that you're gaining oxygen or you're losing hydrogens. Whereas in a reduction reaction, you're losing oxygens or you're gaining hydrogens. So in organic, we tend to use a very simplified definition of oxidation and reduction. Although I see in yesterday's reading, which we didn't quite get to, there is a section in the book on how to calculate the oxidation numbers for carbon, but we normally don't do that. So in this case, I actually do have something that I can count the electrons with. Over here, what happened to my osmium? The pair of electrons went from this double bond to the osmium. So that means the osmium gained electrons, which is reduction, right? Lose electrons, oxidation. So that's Leo the lion goes grr. There's an oil rig one too. This one has stuck in my mind forever. So in this case, because we're using a metal, we can easily see, oh, the metal went reduction. That means the organic molecule had to undergo oxidation. But we also know the organic molecule underwent oxidation because it gained 2 oxygens. So we're not at 2 OHs yet. Osmium is one of those metals that's really expensive, and it would be prohibitively expensive to run this reaction if I had to use 1 mole equivalent of osmium and 1 mole of alkene. So if I had to do these on an equal mole ratio, I couldn't afford to do that. And I can't afford to throw away the osmium. So what you do is you use a small amount of osmium, and then you react the whole molecule with hydrogen peroxide. Now, hydrogen peroxide is an oxidizing reagent. That's what its job is. And so what it's going to do is it's going to cleave the 2 osmium-oxygen bonds, and it's going to restore the osmium to its original catalytic state. And then your organic molecule then will have 2 OHs that added cis because of the original 5-membered ring. So if we just use a catalytic amount of osmium tetroxide, and we have enough hydrogen peroxide in there that it continually regenerates the osmium tetroxide, we can do this reaction efficiently. But one of the things that's going to be difficult, at least initially, to handle is how many different hydrogen peroxides do I see in this list of reagents. I've got it for hydroboration oxidation, I've got it for HBr addition, and I've got it for this osmium. So hydrogen peroxide is kind of a reagent that we use in 3 of these reactions. So its context is going to be important, because if you're looking at it going, oh, well, hydrogen peroxide always does anti-Markovnikov addition. In 2 of the 3 places it does, but in the 3rd place it doesn't. As a matter of fact, it really doesn't play a role other than to regenerate the osmium tetroxide. So what's the reason for 100% cis? It's because we are going through that 5-membered ring intermediate. Two things. There's mechanisms as you're being able to write products for these. So there's 2 different things. As far as the mechanisms go, let's see, which ones would you need to know the mechanisms of? HBr, H plus H2O, Br2, Br2 with water, HBr and peroxide. Those would be the ones that I could potentially ask you mechanisms of, the ones that I starred. The other ones, I've shown you the mechanisms, so if you're learning, memorizing, whatever you want to call it, that each one of those intermediates that it goes through in the mechanism tells you, is it Markovnikov, is it 100% cis or trans? So that's why I'm showing you those intermediates. I mean, I could have left all that out and just said, oh, BH3H2O2, anti-Markovnikov, cis. Remember that, we'll move on. But having the mechanism helps you understand why it's cis and why it's anti-Markovnikov. The rest of them you'll just have to know. And in some of the problems I handed out, which we'll do, you don't need to write the mechanism out for everything. So next week, on Monday, when I give you an exam, I'm going to ask you to do some mechanisms, write them, and then I'm also going to ask you to write the products of these reactions. I'm also going to ask you whether they're regioselective, stereoselective, both, or neither. So if you're like, well, we haven't done that, we will. So I'm pretty sure that that mechanism was in the book. I know it was in the video on that. And so I'm for every class. So tomorrow you'll see in the folder that there is the reading assignment again. There will be a video where if you click on it and go to the YouTube page, it'll tell you what sections, where to start in terms of the time frame to look at that particular topic. And so if you want to watch the video on that, you can. If you want to read the book, which I would suggest, you have to do, whether you want to read that afterwards, go back and reread it after class. Well, I've already asked you to read it before class, so if you want to read it before or after you watch the video, or if you don't want to watch the video at all, if it makes sense from the book, then by all means do that. But I'm trying to give as many options here because I know people have a preference or effectiveness one way or another. So there is a video, and actually the way it's cut up, you don't have to watch all 45 minutes. You can just watch like a 5 or 6 minute segment. Don't ask me to do that with all of them because then I have to cut them apart, and it's easy for me to put a timestamp in the description. I don't think it gets monetized then, but it's not getting monetized anyway because it's in an educational account, which is why it can have an hour's worth of video. So, does that make sense for the osmium? So what's the KMNO4, just to complete the picture? What's the KMNO4 going to do? Same thing. So if I take my double bond and I react it now with the KMNO4, the KMNO4 has to have an O- to counterion the potassium for the counterion there. So this is what the KMNO4 would look like, and this reaction is going to do exactly the same thing. It's going to go, pair of electrons moves from the double bond to form the CO bond. Pair of electrons moves into the manganese, therefore reducing it, and then the pair of electrons from the manganese oxygen double bond is going to go out to form the 5-membered ring. So potassium permanganate does exactly the same thing mechanistically. So we're going to end up with a 5-membered ring. And so we're still going to set the stereochemistry at being cis. Only in this case, potassium permanganate is like dirt cheap. If you've used it in General Chem Lab, it's the purple stuff that makes the dark purple solution. Usually you titrate that with iron, or you titrate iron with it. If you have a fish tank and you want your fish tank's like kind of cloudy and stuff, you add a couple drops of a dilute permanganate solution, and the permanganate goes in and reacts with all of the fish waste and other stuff, and it oxidizes it. And when it oxidizes it, that means it puts OH groups on it. And as it puts OH groups on it, that makes all that sediment and stuff that's making your tank cloudy water soluble, so that it becomes clear. So it's used as a, and if you use just a little bit, you don't kill the fish, but you like decloud the tank. And so permanganate's dirt cheap, but if we use permanganate with hydroxide, then the hydroxide is going to come in again, cleave those manganese oxygen bonds, so that I'm going to end up with now my cis OH groups, and in this case I'm going to end up forming MnO2, which is manganese dioxide, which forms a brown precipitate. In the lab class, we're going to do a permanganate oxidation, and we're going to watch the purple color disappear and the brown precipitate form. And we're going to actually wash the product to make sure that there's no purple in it, because that would be permanganate. So we're actually going to do one of these oxidations with potassium permanganate in the lab class. But that's what you look for, is the brown precipitate. So those two are the methods for hydroxylating. So there's the chart. Probably needs to be copied into a much neater form. Perhaps even flashcards would be helpful. Okay, I was going to talk about flashcards yesterday. Let me take a little bit of a diversion here. Everybody has their own system, right? For organizing materials. If you don't have a system for organizing materials, you should probably invest in one, because organization is probably the key thing in terms of the amount of material that we're going to go through. So keeping up on it and getting it organized both on paper and in here. I mean, you can argue in here's the most important, but you're going to find that you probably want it on paper first. That's going to be critical. So everybody has their own system, whether you want to make it on sheets of paper, whether you want to use, I don't know, Quizlet, or there's other things on the iPad you can use. I guess there's it starts with A. It's not a Kindi, that's something else. One of our students that went to medical school just raved it, or who was in medical school was just raving about this program. If you want the app, you have to pay for it, but if you want it on the computer, it's free. Anything like that, that's up, you know, that's kind of your system. And if there's one thing I've learned through the years, I don't mess with students' systems because they yell at me. I had a research student. She's like, "Don't mess with my system. I got this set up the way I want it. Don't mess with it." To back off there. I don't have it on here, but I do have it on here. I just can't see it. So any way you want to organize this stuff is fine. But if you were thinking about a 3x5 card system or a piece of paper system, my suggestion is something like this. That you start with, let's say we start with a double bond, and let's say I add H2 with palladium on it, and I put the arrow there on the front of the card. My suggestion on the back of the card would be to do this. To have the double bond, the arrow, and have the back of the card look like that. Now, why would I suggest doing that? Because we're going to have to get to a point where it's not good enough to just be able to think forwards direction. We're going to have to begin to think in the backwards direction. So thinking in the backwards direction would be, I want to convert a double bond into an alkane. How do I do it? And so saying, okay, well, let's see, I need hydrogen and palladium. Learning the reagent that goes with the transformation is going to be equally important as knowing what the final product is. So if you had cards that had on the front the reactants and on the back the reactant and the final product, you could then, when you're done with them, flip them over and test yourself on the reagent. Would be the way to go. Again, everybody has their own system. My suggestion is the simpler you make these, the better off you'll be. Because you can, I think you can buy 3x5 cards, or you used to be able to back in the day. And I think I have some in my office. But the problem is, it's a page of the textbook on a card. Well, that's not great for review. For review, you want something you can flip through on a daily basis, or as every other day basis, so that you can begin to remember and learn these reactions. And if we spend a lot of time going from A to B to C to D to E, in other words, taking molecule A, doing a reaction to get to B, reacting that to get to C, reacting that to get to D, and reacting that to get to E, there are other things you might put on this card, including, overall, this is a reduction of an alkene. So you can tweak that whatever way you want. You can do things without paper. But one of the things that I notice is that organization is sometimes really helpful. And that's going to help. If you have everything organized going into the day before the exam, then you're going to be more reviewing than you are cramming. Because I have had students walk in my office with a folder, not a 3-ring binder, a folder. And it's not even a hot mess, it's a mess. Papers are everywhere, and I'm like, okay, first thing you need to do is you need to get this organized so that you know what you need to study for the exam. And so if you can get in the habit of doing that, I think it'll help you spend more time on learning than actually having to reorganize everything. But again, you have your own system, and hopefully it's successful. But those would be my suggestions. So that's the table. Any questions on the alkynes? Okay. So, any questions on the oxidation numbers of carbon? So if I gave you that molecule and said, what's the oxidation numbers of the carbon, what would you say? What? Carbon is +2. What is it in this molecule? Well, formal charge is 0. The oxidation number could be 0 too. What kind of reaction is that? Oxidation or reduction? What? So what should happen to the oxidation number of the carbon? If this is oxidation, that means the carbon should be losing electrons, which means their oxidation number should go up, should increase. All right, well now all I need to know is I just need to know the oxidation numbers of those two carbons. Anybody tell me how to do that? Are you going to tell me how to do that, or did you have a question? You can jump in if she gets stuck. Okay? How are we going to do this? Okay, so what are the hydrogen's oxidation number then? +1? I like +1. Okay. Then on the other side, what do we got? Same thing. How about in the double bond case? +2 for the carbons and... No, not +2 for the carbons. What for the carbons? -2 for the carbons and +1s for the hydrogen. Okay, so what happened to the oxidation number? Basically, what did I do? I lost an electron to go from -3. I lost an electron to go from -3 to -2, and I've got 2 carbons doing that, so basically I lost 2 electrons overall. And so this is oxidation. because the carbon's -3. No. Almost always I'll buy, but not always. Sure. There's our borohydride from yesterday. And in this case, boron is less electronegative than hydrogen is, because it's like one of those metalloids. So in this case, the hydrogens would all be -1. Hence the name borohydride. Hydride means H with a -1. Will we be in that situation? Yes. Because if I use something like potassium hydride, where the potassium is plus and the hydride is minus, back in general chemistry, I bet if you talked about hydrogen, you'll say the exception to hydrogen being +1 is when it's attached to a metal. And so then it becomes -1. In this class, that's going to be a great base, and it's going to be a great nucleophile, H-. So will we use that? Yes. Okay, now that you've seen how it's done, what if I had formaldehyde, which is on the left, the C double bond O with an H is an aldehyde functional group, and I wanted to convert that into methyl alcohol. What's the oxidation number of each of the carbons? And is the overall reaction oxidation or reduction? Yeah. In this case, boron would be a +4. Sorry, +3. It's +3 because overall, a borohydride is a -1 ion. So it's BH4-. And so each hydrogen is a -1. That would put the boron as a +3. Oxygen -2 for which one? Which carbon? 0. I'm not writing anything. What's the carbon in the carbonyl? You're right, it's 0. No, you're right, it's 0. What's the carbon on the other side? No. What? -2? What's the oxygen? No, I like -2.
Why is it?
Good question. I think the bigger question as I'm looking around is like, does anybody have the question like, what the hell are you doing? What?
What the hell are you doing?
Anybody completely lost? Okay. So, this, I've been doing this a long time. Every day is a little bit longer. So, I have this kind of sense that, wow, nobody knows how to do this. But that didn't stop me from plowing on, did it? So you have to say, oh, stop, what are you doing? Where do these numbers come from? So, the first thing is, with these oxidation numbers, these are not going to be calculated the same way that we calculate oxidation numbers in general chemistry. Except there is one part that is the same. And that is, if somebody said all the hydrogens are +1, they are. Except over here in this case. So for an organic molecule, you can make the hydrogens all +1. And so if these two were +1 and this oxygen was -2, and how does it -2? I'll get to that in a minute. Then +1 +1 -2, then that means for this overall molecule to be 0, the carbon has to be 0. So our first overriding rule is that all the oxidation numbers, when they add up, they have to add up to the formal charge on that molecule. And if that formal charge is 0, they have to add up to 0. Right, now that's like general chemistry rule. And the other general chemistry rule is that hydrogen is +1 except when it's attached to a boron or a metal. So, here's how we do this. Or maybe somebody else can tell me how they did it, and I'll modify. So, why is the oxygen -2 here? No. Because the oxidation number is actually defined a little bit differently here. Now you could say, but on the periodic table, I remember oxygen is always -2, except when it's hydrogen peroxide where it's -1. But in an organic molecule, how do we get that oxygen being -2? No, go on. I haven't attacked anybody, right? I haven't humiliated anybody for answering the question wrong, right?
Does it have something to do with the fact that there's 2 bonds?
Yes, it does. So that means that each one of those bonds, the oxygen is getting a -1. So there's 2 bonds at -1 each. So how does the oxygen get the -1? Okay, it deals with the sharing of the electrons in that bond. Now, this is a polar covalent bond, correct? Covalent meaning that it's shared, polar meaning that it's unequal sharing. When we determine the oxidation number in an organic molecule, we basically say there is no sharing. We're going to say the most electronegative element in that bond gets that electron, takes the electron away from the other. So in each one of these bonds, oxygen owns 1. It shares 2, but if I'm going to do oxidation number, I'm going to give both of those electrons to the oxygen. So that means that in each one of those bonds, it's going to have a -1 because it's gaining 1 electron from each one of those bonds. It's taking that electron from carbon in each one of those bonds. So there is no sharing. So that means if oxygen's taking away 1 electron in each of those bonds, there's 2 bonds, that means the net result is that that oxygen is -2. Over here with the methanol, looking at the oxygen and the methanol. Oxygen-hydrogen bond, which one is more electronegative? Oxygen, so it's going to take away 1 electron from the hydrogen. Oxygen-carbon bond, what's it going to do? Same thing, so now I've got 2 -1 charges, which means that overall the oxygen is -2, because it took away 1 electron from the hydrogen, 1 electron from the carbon. Is this real? No, but oxidation numbers are, they're kind of accounting terms. So in this case, that's why the oxygen is -2 in each one of these cases, because it's taking away 1 electron per bond from the atom it's attached to, because it's more electronegative than that atom. So what about the hydrogen over here attached to the oxygen? It lost its electron to oxygen, so it's going to have a +1 charge. How about this carbon? How about this carbon down here in the carbonyl, in the C double bond O? It lost both of its electrons to carbon, right? Or oxygen. So that's going to give it a +2. Except now let's look at the CH bonds. So who's more electronegative, carbon or hydrogen? Carbon. And so now each one of those hydrogens is going to give up an electron to the carbon. So now it's +2 because it lost 2, but then it gained 2 from the hydrogen, so its net result is it's 0. And how about the hydrogens? The hydrogens are +1. So when we do an oxidation number, we're eliminating sharing. We're saying, look at each bond. The most electronegative element in the bond gets an electron. So over here, what about this carbon? Well, if you don't want to do the math, do this. +1, +1, +1. The carbon was -2. That means, let's see, we've got a -2 and 4 +1s. So that means this carbon has to be -2. So now we've got -2, -2, and 4 +1s. So it adds up to 0. Now, why is this carbon -1 or -2? It's gaining 1 from each of the three hydrogens, right? So it's -3. But then it just lost one of those to the oxygen. So its net result is it's -2. And then for this reaction, what kind of reaction is this? Reduction, because it's gaining 2 hydrogens. Does the change in oxygen tell me that? It's going from 0 to -2, so what's it doing? Gaining electrons. So it's gaining 2 electrons, which means it's reduction. So we do oxidation number in organic a little bit differently. At least I do it differently, in terms of just taking each bond Now, if you have a carbon attached to a carbon, they have the same electronegativity. There's no transfer of electrons. Again, is this transfer of electrons real? No. This is just an accounting tool. So actually now we could calculate the oxidation numbers. We don't necessarily have to remember that addition of hydrogens is reduction, loss of oxygens is reduction, gain of oxygen is oxidation, or loss of hydrogen would be oxidation. But I like those because they're quick and easy. Does that make sense? So if I do a problem and, I have no idea, raise your hand. Because you're probably not the only one that doesn't get it. And there are times when I'm going to ask, like I'm going to say, I wonder if they really read through that section of the book. Or any sections of the book. And the book on flipping the lectures is, if people didn't read, ignore them. They'll get the hint that they should be reading before class, or they won't be a problem. It's a pretty harsh book. It's tough to do. Any other questions about anything in the... So, Sis hydroxylation, let me just give you the... If you're curious, what's the difference between cis and syn? So cis, I'm assuming somebody's curious. So cis really should refer to systems that that have no conformational mobility. Meaning that if you have a non-cyclic system or a system without a double bond, I have relatively free rotation around the double bond. So saying that those two OH groups are cis is technically incorrect because I could rotate them around. Saying that the two OH groups are cis in a cyclic system or in a carbon-carbon double bond where there is no rotational possibility, then these cis would be the appropriate term. Saying those two OHs are cis because they're always going to be cis because I have nothing to rotate. I can rotate the cyclohexane ring all I want, but those OH groups are never going to change from being cis to trans. In a system that's acyclic, we would actually call those two OH groups syn, meaning that they're going to be on the same side. I can make a conformation where they're on the same side. Of course, I can also make a conformation if I rotate around it where they're opposite each other as well, which would be anti. So syn and anti are kind of the acyclic equivalents of cis and trans in a system. So when they're calling it Sis hydroxylation, they're actually using the broadest term because they're saying you could do this reaction without a ring or with a ring. No.
And so the alkyne
Right. So cis would be appropriate for either one of these two molecules, but calling this cis, calling this acyclic system cis there would be a lot of people that would say, don't do that. But I will still probably call this cis hydroxylation. Because that's not true. Most times we're going to be seeing this as being cis when we're doing the reaction with an alkene that's in a ring, because that's when we're going to see the two OH groups. So an anti-Markovnikov, and then alkynes. And then the big thing about alkynes is alkylating alkynyl anions and then doing eliminations to form alkynes. And then putting all the alkene reactions together. What? So you want to make one, or you want to react one? Tomorrow is all the alkyne reactions, all the addition reactions. Today it's just making an alkyne and making an alkynyl anion and reacting it. The alkynyl anion, okay? I want to make that alkynyl anion. There's two questions for you. So there's your questions. Okay. Anybody have all the answers to those? No? Okay. So here's what we're going to do. I have... How do I have... There's 11 people. How do I have 4 groups of 3? Okay, that's interesting. Here's what we're going to do. We're going to break up into groups. We'll take our 5-minute break, and then we'll break up into groups, and then I want you to answer those questions. Also, no, we'll go around, and then and see how we're gonna do on these. So I've got groups of Kaylee, Sydney. Oh, that's right, 'cause Sydney's not here anymore. How's Sydney still in here? Let me regroup. No. I'm gonna regroup, okay. No. Let me regroup. Let me put, let's see, groups of 3 or 4. Let's see. Okay, we've got Nell, Hannah, and Megan. Kaylee, Alex, and Aria, sorry. And then Max, Greg, and Cameron, and then Brandon and Eleanor. So so you can rearrange yourselves to be in those groups, and then work on these questions, and I'll walk around. At some point my phone's gonna go off and I gotta go deal with an engineer for a few minutes, but and don't worry if you get these problems done, I got more. Did you get it? This is what I realized. So it would be so it's on the second page is what I'm at, is the using acetylide ions.
We did the whole
table of polybases and stuff.
Yeah, one was like using NH2.
Right. Oh, you could use
your hydrogen peroxide. So, like, because in the reading it would give you this, right?
Right.
And then you had this, and then there was another molecule, and another molecule, and then you had to choose from the different reagents.
Right. So So we're going to use NH2 minus as a strong base.
Right.
That's going to deprotonate that.
For what, later on, or for this?
For this one. So in the box, the it should go NH2 minus.
Not the hydrogen peroxide.
No, because all I'm doing is deprotonating.
Right. Yeah. This is a oxidation reaction. If you use the hydrogen.
Yeah, but that's not oxidation.
I mean,
you might have to go back and take a look at your notes and see. But this is the acetylide ions.
Yeah. And then there's- yeah, now I'm just thinking it's
On the periodic table, N minus is stronger than O minus. You could use a C minus for this because it's even stronger, but you have to know how to make a C minus. You'll know that tomorrow because that's in the reading for tonight. So what kind of reaction is this? This is an acid-base reaction. And we're using the NH2 minus. So what was the mechanism for the first reaction? SN2. Why? Because this is a strong nucleophile plus a secondary halide. So that's going to be SN2. So the negative is going to come in, kick off the chlorine. And so we're going to end up with those two groups. There's an H here. And then we're going to end up with the C triple bond C with the ethyl group on that side. So that's horrible looking. That's better. So that's SN2. So the critical part here is that the triple bond is both a strong nucleophile and a strong base, particularly if you're considering that it took an NH2 minus to deprotonate it to make that C minus. So now I have a strong nucleophile that wants to react with this tertiary halide. And it wants to do an SN2 reaction, and can it? No. Because nucleophiles can't do SN2 on a tertiary halide. Agreed? So we can't do SN2. So then what happens? What happens is this is both a strong nucleophile and a strong base. So it has a dual personality. Whenever we have these, and this is the first one of these we've encountered, that's a strong nucleophile and a strong base, what it's going to do is if it can't react as a nucleophile, it immediately goes into base mode. And so if it goes into base mode, that means E2. I mean, I have other ways. You know, if we give these things personalities, it's like it wanted to be a nucleophile, it gets angry, and then it goes, well, the hell with it. I'm just going to do E2 and rip a base, or rip a hydrogen off. And that's what it does. That's what these things do. This is the first one of these, though, we've encountered. So then we have an E2 reaction. So what do we have to do? We got to figure out our alpha carbon, our beta carbon, and our other beta carbon, because we have two possible products of this reaction. We could have the double bond inside the ring, or we could have the double bond outside the ring. And you could say, well, what about the other double bond that's inside the ring? So what about these two molecules? They are the same. No?
Well, I was just gonna ask, how do you know that it wouldn't have done SN1?
How do you know if it wouldn't have done SN1? Because there's sort of an unwritten rule that you don't know, but now you do. That whenever you have something that's a strong base that can do E2, it either does SN2 or E2. That's it. So if it can't do a nucleophilic attack, it's going to react fast and rip a hydrogen off before the molecule could lose the leaving group and go through that. So the whole idea of this is it introduces the new thing, the new idea that for primaries and secondaries, it's easy to react alkynyl anions and do SN2. For tertiaries, it's going to do E2. So these are the same products. Which one's the major product of those alkenes, having a double bond in the ring or outside the ring? Well, if we say inside the ring, then we're treating this alkynyl anion as if it was like an NH2 minus. If we say outside the ring, then we're treating it like a tertiary peroxide. So the question is this base sterically hindered or not? Now, a lot of people, when they looked at it, immediately said, well, yeah, it's sterically hindered. But remember, this is a linear geometry here. And so there's not really a lot of steric hindrance around the C minus. It's linear. And so it's going to act more like an NH2 minus, which means the more substituted products are going to be the major products. Everybody okay with that so far? Then the other reaction of an alkynyl anion is with a carbonyl. Now this is new. And if, we're looking at this going, I don't know what to do. Well, what do I know about this? It's a strong nucleophile. So what does it want to react with? And an electrophile. So is there part of this carbon-oxygen double bond that's electrophilic? Yes. Because in the polar covalent bond, the carbon is delta plus and the oxygen is delta minus. So what if we take this pair of electrons and come over here and form a carbon-carbon bond? Right. If I don't do something, I'm going to have 5 bonds to the carbon. So what can I do? How about I move this pair of electrons from the double bond up to the oxygen? Now, first of all, is that electron, are those electrons moving in the correct direction? And what do I mean by correct direction? I mean the atom in that bond that's more electronegative is getting the electrons. Yes, because the oxygen is more electronegative. So that pair of electrons is going to the oxygen, that's okay. If I tried to move the pair of electrons to the atom that was less electronegative, I'd have a problem. So I'm going to form my carbon-carbon bond. And I'm going to have my O with my 3 lone pairs now, which makes that negative. So I have an alkoxide ion. And that alkoxide ion, in order to get me back to neutral, what do I have to do to it? Add H2O. What dissolved in H2O? H plus. So if I add acid and water, just H plus, now my alkoxide gets protonated, and now I have my final product. So there's my final product. I made what's called an alkynyl alcohol. Does this have a name? It is not SN1, SN2, E1, or E2. It is called like acyl addition. Acyl means a carbon-carbon or carbon-oxygen double bond. Oh, this is the easiest mechanism I could give you on an exam. Because it's like 2 steps. Would you have to show this? Yes. Yes. I mean, this is a really nice mechanism for an exam because it's 2 steps, right to the point. Which means I probably won't ask it of you, but. Now, what you could say, this seems like this reaction's coming out of left field. No, it's not. It's foreshadowing. Because what you're going to look at for tomorrow are Grignard reactions. And a Grignard reaction is when you make an R-, when you make a carbanion. And any carbanion, any R-, including this, will react with a carbonyl in this mechanism to make an alcohol. So this is just one of many reactions that you'll do for tomorrow. So, does that kind of make sense? So particularly with the alkynyl anions, they can react, if they react with primaries and secondary halides, you're going to end up adding an alkyl group to the end of the alkyne. If it's a tertiary halide, you're going to end up doing E2, and if you do E2, you're going to form the most substituted product. If you react it with a carbonyl, right now that's like, oh no, that's a new reaction again. By tomorrow, there's going to be 6 more of those that are exactly like this. So tomorrow will be like, oh yeah, we're going to add it to a carbonyl, we add it to the carbon, we make the O-. The only other thing with alkynes was, how do we make them? How do you make an alkyne? You can start with an alkene. So let's make this a take-home quiz for tomorrow. What goes in the boxes? So this is your take-home. This is the take-home quiz for tomorrow. Just on a separate piece of paper, write what goes in write the structures that go in the boxes. And the hint is, there better be a triple bond in the final box, because this is a way to make an alkyne. Right. So then tomorrow, you're reading watching whatever assignment is the sections for tomorrow that's on your, that are in the reading list as well as online. So it deals with reactions of alkynes. You should have some deja vu with reactions of alkynes because they're just reactions of alkenes twice because there's 2 pi bonds. And then also, review of making alcohols. Oh, won't that be fun? And then Grignard reactions. Okay. So as you're going through, write down questions. Like I said, we'll start with questions. I won't jump into any review. I'll answer your questions and then we'll break up into groups and do some more problem sets. Okay. If you have any questions, shoot me an email. Otherwise, I will see you tomorrow.